Hi everyone, this is Ron Baden with Atlanta Functional Programming. Welcome to another episode of the Common Lisp Study Group. Today we're going to be continuing our discussion and exploration of the Lisp interface library. As I mentioned last time, with the Lisp interface library is a library that was built by Francois Rudeau back in like 2012. It's a fairly mature library that implements a series of data structures and a design methodology that the author has dubbed the interface passing style. It's a style that allows you to write algorithms in a generic enough way that would separate the implementation details as to whether or not the underlying data structures upon which those algorithms are operating on are whether or not they're pure or stateful objects, as well as providing you some abilities to do some compositional things that you will normally typically see in statically typed languages such as Haskell, ML, OCaml, or even C++. The interface passing style, as I mentioned last time, kind of allowed you to do many of these things from those other languages and provides you an ability to create data structures and other algorithms that you can use in a very generic fashion. Last time when we convened and started exploring this library, we had an example of how might one use this library. We started exploring some of the implementations of the A-list interface, and we explored kind of a stumbling block that I at least had initially when I was looking at this library, particularly how to look up something and change between implementations. And it was this example here that is indicated on line 19 through 22, where one might be looking up, in an associative list for a particular key. Now, a couple of things. Last time, this was originally implemented like pure A-list lookup, and this here. Oops, my apologies. I forgot to load. The Lisp interface library. Okay, so let's go back to what I was saying before. So last time we had this example that basically allowed you to, look up in a concrete way using a pure list, A-list implementation of looking up in an associative list for a given key across a very simple data structure. Now, if we wanted to generalize this and allow us some flexibility, one of the things that I was mentioning is that you could switch the interfaces to something else so that you can use a different implementation. There's a couple of mistakes there that I want to first rectify. One is the lookup method upon you are dispatching on. So typically you'd want to look at all the available functions that are in what's in the top level package, which is Lisp interface, lil/interface/all. This is the top level exported library for all generic functions and interfaces that are abstract enough that you can go and switch and implement some of them on your own. Now, this should not be confused with interface/base, because interface/base is a much lower level. It has some of the same interfaces as interface/all, but it does not have everything. And from my exploration, it became clear that what we wanted is to use the generic functions that are defined in interface/all, but provide our own implementation details as the second argument, which is the same as the pure version, which is why there was a little bit of confusion there. This, as as many of you can see, if just check one thing here. Let me see if I can actually increase mini buffer size. Well, it was, let's be a way to go into here. Increase. Oh, oops. Sorry. Fine. I can't do anything here. Yeah, there we go. That's what I wanted. Let me see if I could do that here. No, that didn't work. Okay, sorry folks. Folks who can't read my mini buffer, I will try and best show you what the arguments are. Please look at please refer to the documentation for further information. Right now, I'm not entirely sure how to set that up again. I should I'm making a note to actually go and increase it later on. Anyway, so as mentioned last time, the lookup, a lot of these generic functions, lookup is one example of a generic function that's part of the Lisp interface library, has the first argument is the interface that upon you are actually providing an instance to check some invariants on. A couple things about this, just a quick review on what I mentioned last time, but we're going to dig a little deeper today. The interfaces themselves are what we are dispatching on. They are the first argument. A couple of functions might dispatch on one or more interfaces. It's a very rare occasion that you will see multiple interfaces as part of a generic algorithm definition, primarily because of the fact that oftentimes what will happen is that will clutter up the intent of the algorithm itself. So what they would do is they would combine them and create a higher level interface, taking advantage of the common Lisp object system and inheritance to actually go and create a super interface, so to speak. One thing to note also, and we saw this with the example of A-list, particularly each interface itself could be an abstract interface. Let me just pull up that for sake of example. And that is, let's see here, I have it open, list implementation, this one. All right, so this interface, which is available for folks who are watching in, is it's actually in the source code when you download through Quick Lisp, the Lisp interface library. It takes on multiple interfaces, some of which might be available as part of some of which may be abstract, some of which may be concrete. In this case, since A-list itself is a concrete implementation of a bunch of abstract interfaces, you will notice that it does not have a couple things, which is one of which is mainly the abstract keyword. An example of that is, and I'm going to go ahead and show you that, is the map interface. I think is the best one. Let's do that. Yeah. So we look at the map interface here as an example. You'll see that, again, to review, we're defining the interface using Lisp interfaces implementation of the define interface macro, which itself is nothing more than a high level. It generates essentially like a def class, but not too much to go beyond that. it adds a couple of additional options, which we will go through here. As you can see here, the first argument is obviously the name, as we mentioned last time. Second argument is going to be a list of a list of interfaces that may or not be implemented by this guy. It should implement most of the functions. Some of these interfaces that are part of the library itself is related to mixins. Actually, they implement some portion of potentially of a higher level generic algorithm that's common across multiple implementations of the same concrete interface. So an example of this is if you need to do balancing trees, there are interfaces already available in the Lisp interface library that implements the common functionality that's normally associated with different balancing trees, although the balancing acts might change a little bit here or there, and you could override those using the def method syntax just to implement a more specific version of your balancing. And thanks to method combination, that will usually be picked up before the rest of it. The third argument in the interface stuff, which we did not touch base last time, just mainly because the A-list implementation didn't have it, but this one does, is this keyword right here. This keyword right here, the abstract keyword, basically tells the Lisp interface library, and it generates some functions on this. It creates it doesn't allow essentially the library itself to instantiate this interface. It basically throws that error that we saw earlier last time, which is pure map : map is unbound. That basically means that, it should tell you that you are accidentally probably instantiating an abstract interface and not a concrete one. Now, why is that important with respect to the usage of these algorithms? Well, one of the things about the Lisp interface library, and one of the challenges that it had when it was trying to overcome when it was being designed, was the fact that Common Lisp doesn't do it's dynamically typed, right? It does a lot of invariant checking at runtime, and as a result of this, sometimes when you're passing in an instance of an object, or you're constructing an instance of an object that is of this particular map interface type, it's going to try and construct or look up in its machinery the available concrete instance of that map. Now, if it has the abstract keyword provided, what ends up happening is it recognizes that this should not be instantiated at runtime and throws that error. Now, if it had a concrete version of this, and you did something like passing in an object instance that does not adhere to the interface itself, what ends up happening is that it will also throw up a runtime error when you're trying to develop. Now, obviously, that might come a little bit at a disadvantage for folks coming in from statically typed languages, because normally you would say, well, we compiled this guy. It shouldn't have compiled in the first place. You have thrown an error at compile time. Well, because it's dynamically typed, it doesn't do any sort of invariant checking. Now, I'm saying that only lightly. I'm not saying that it's not available. There is a function in the Lisp interface library, which we'll touch base in later on, called check invariant, that allows you to do that kind of very detailed checking. But according to the author in the documentation, it's a very expensive check. So you can certainly use it while you're developing your own interfaces, or you're using existing interfaces with concrete implementations and designing your algorithms and creating libraries and so forth. But when you're going into production code, it is suggested that you do not provide or do not use that check invariant in your code directly, because it doesn't buy you anything. It's just an expensive runtime check that will give you safer code, but at the expense of some performance hits. Since you get some of that for free when you end up using the safety 3 when you're compiling, in some cases, as long as you are not blatantly passing in incorrect types, you should be good. So we've already covered the majority of this stuff about def generic and def thing. I just wanted to briefly mention abstract because I know that we haven't touched base on that too much last time. But I wanted to mention that and give you some examples of this mix-in implementation thing that they provided in the library that I found interesting last week that I didn't have time to cover. So now we've talked about the generic algorithm, the interfaces, and this implementation. What about what we were talking about, the challenge that we hit last time about switching this to a different implementation? Well, like I said earlier, we had to switch this from pure A-list : lookup to interface all lookup. Now we can actually switch to the interface. There is another thing that we need to do, which is obviously change the argument here so that it can take in something else. Now, one thing that I will say that I haven't found yet. So I'm going to give a slightly different example, just mainly because of the fact that I could not find a concrete implementation of this particular example in the library. It may not actually exist. But let's change this implementation example just so that I could show you how different implementations might work. Instead of using symbols and has the keys to this associative list, let's change these to numbers, right? So our key is numbers here. Okay. This isn't changing much from what we saw last time. We're just basically looking for year, but we have now an encoding essentially, right? So now we can see that we're still getting what we had before, which is we were looking up the year for this A-list structure. We had to encode it into some things. And obviously you could certainly do this by creating, like, say, def constants, like this for the second name 1, def constant year 2. I'm not suggesting that you go ahead and do this. I'm just using this for the sake of example, just so that we don't have to repeat ourselves here and we can have somewhat the same kind of code that we had last time. Topic name, topic key, history. Okay, let's go ahead and do this. Oh, sorry. MCR. So now that's all. Oh, sorry, not MCF. MCR. There we go. That's it. So we have now our topic key. Cool. So we're just going to go ahead and replace this to name key, year key. I hope this actually works, because since it's a quoted list, I'm not sure if it's going to grab it or not, but we'll see. Nothing. Yeah, that's what I thought. This is going to only allow me to use this. There we go. So let's say that we want to change this to, instead of being an associative list with a number has the key and the value being whatever, right? Let's change this into a map, okay? Some sort of hash map of some sort, okay? Well, there's two hash maps, there's several hash map implementations inside the Lisp interface library, but The one that we're going to particularly use for is actually just its typical map data structure, and we'll go look at its implementation after I show you this. And that is going to be the number map. Number map basically is nothing more, as the name stands for. Number is the representation of the key interface, and again, we'll revisit the map interface that we saw earlier so that I could go through those things in specifics. But in order for us to do this sort of conversion, we need to first convert this associative list, because we're not going to actually go and it may not be the case especially in production code. You might end up getting a data structure that is of one particular type. You might need to convert it so that you can use algorithms of another particular type. In this case, what we're going to use is, and we tried using this last time, is the A-list map implementation function, which takes in a map interface and then constructs a new instance of that map. Now, there's a couple things here that you need to be aware of. We are not only supposed to be doing this, okay? Stateful, no, don't need to be stateful. We'll use pure tree. So the map interface that we're using, which is number map, is available in lil pure tree :number map. Now, there's a stateful version of this number map, which means you can mutate it, as well as a pure version. And since we're dealing with right now all the functional data structures, to give you an overview of the library, I thought it would be better to just first go through that. Now, the other thing that we need to change here is the interface that we're actually passing to the actual lookup. And the reason for this, we have to do both, is because this is going to expect one particular type of way of implementing some of the interfaces that lookup requires. Not changing this, you'll end up getting something like this, which is lil pure AVL tree node is not of type list. And the reason for that is because it isn't of type list. It's actually a different object altogether. So we need to go and change that, and we need to just make sure that we pass this number map. And as soon as we do that, we'll see that we end up getting the same sort of implementation that we had before. Now, the first question that many you might ask is, well, why can't we just pass in this in the first place like we did last time? Wouldn't that be just better, because that's more generic than what you had before, which is a more concrete implementation of the key interface? Well, a couple of problems here. Internally, lookup, and it's related to how lookup is defined in defined interface method, but lookup already takes this map as a top-level class, all right? And as I've shown you, map itself is a abstract interface. So all the methods have already been casted in such a way that this abstract interface can be dispatched on, okay, number one. But another thing, and this is more important to how the machinery works in the interface library, is that the second argument here, which is our actual object, okay, that we've constructed using A-list and a concrete implementation of this, okay, this is not actually constructing the interface object that is required by lookup in order to make sure that the interfaces all match up, okay? So this goes back to one of the design principles of the Lisp interface library, which is interfaces are first-class objects. They are explicitly passed around like arguments. This is very different from other languages where you can, at compile time, implement an interface. The type checker will say, okay, this adheres to this interface. I'm going to go ahead and use this, all right? Since it's all happening in the runtime, we're passing the contract around, the interface around. So there needs to be a instance of this interface to being available. All right, and I'm saying instance in the object-oriented sense mainly because, again, these interfaces are essentially treated like a class hierarchy. Okay, so for lack of a better term, I'm using this. So folks coming from other languages, if you're hearing this phrase and getting a little confused, thinking, oh, interfaces can't be instantiated. This is crazy. What are you talking about? Why are you saying this? It's because of the fact that in the Lisp interface library, the interface objects themselves are actual instances of metaclasses. Okay, specifically the interface class, and they are getting instantiated prior to being dispatched on. So in the case of maps, this map is, at the time of lookup, is expecting an instantiation, an instantiated version of itself, not the abstract version. So if you do this, you're going to get this error saying that it's unbound, because what's happening behind the scenes is the Lisp interface machinery is looking at that interface essentially. And there's one thing that I'm going to mention here about construction of these interfaces, just so that it's confused. There's no confusion. There's a couple of things about the machinery on how it constructs these interfaces. They'll give you some speed ups, but the bottom line is the machinery itself will take this interface object, look it up, see if it's already a constructed object. If it's not a constructed object, it'll construct it. If it is already a constructed object, then it just retrieves the memoized version of that interface object and then just dispatches on it. Okay, I know that's a lot of detail about it, but I'm just giving you, from my experiences, some of these common stumbling blocks that I've been hitting as I've been exploring this library. All right, so we need to pass in a concrete version of this interface. So let's pass in number map. Once we do that, you'll see that this number map is actually correctly adhering to the interface that requires a lookup, and we end up getting what we expect, which is this year key. I'm going to briefly stop for a moment and ask, are there questions on this? I know I threw a lot here about it. I'm just trying to clear up what we had last time specifically, just so that it's a little bit clearer on how this kind of top level design works. Okay, let me just check to see if there's anybody. All right. So what are these concrete interfaces? Okay, I think it's important for us to explore what these are. All right, let's take the example that we just saw here, which is the number map example. Okay. To begin with, we need to go back to the map implementation interface definition that we saw earlier. And you could see that, again, this is an abstract interface with a bunch of generic methods defining the API upon which all maps should implement. So this includes things like insert, drop key, update key, decons, which allows you to drop an association, different map functions, and so forth. Now, notice nowhere in here does it actually mention how does it handle key values, right? For that, we have to actually go to the interface implementation of this guy, which I have to go to map.ls. interface/map. This is the top level interface upon all finite collections are implemented. And this brings us to the second piece and second feature of this library, so to speak. Interesting. This does not have. I thought it would have. Interesting. Let me. Looks like this was implemented slightly more differently than A-list. Let's go back to A-list to just indicate one more feature here, which is the parameterization. But okay, I'll bring that up in later. So we start with this top level map implementation. You see that it's defined as a finite collection. It has generic methods for determining the types of values that are in the map. It allows you to look up particular values in the map. It allows you to grab the first key value in the map to determine if there was if the map was empty or not, essentially, so you can implement whether or not this is an empty or not map. And it has two conversion methods to convert between itself and A-list map. Okay. Main reason this is here is mainly because of the fact that if you go and look at the A-list interface implementation, it does have a concrete version on how to convert this to different versions of itself, and vice versa through the different things. Again, folks looking at this saying, what are the monoids being stuck in this library? We are not touching base on monoids just yet. That's later on in our exploration of this library. So ignore those for just now. But with this map, what we can then do is we can actually go and look at pure map.lisp. And this guy basically implements this top level things. Again, this is yet another abstract interface implementing this. First question that you can notice is this has more methods than the top level map interface provides. Obviously, that's fine, since this is a subclass of that map. You could add multiple methods, more specific methods to other subclass hierarchies, which means you could, if you're writing just a pure version of a map structure, you could just use this guy and not use a top level map structure, and you'll get everything for free. You'll get the lookups for the hookup for free, so you don't have to write your own lookup implementation. And in addition to that, you could just write more specific things on this. So from here, we have two abstract interfaces, and we can then go to essentially number map, which if I can just do this, number tree, that's right, tree, would it be in tree implementation of Lisp? Don't think so, but let's see, number map. So this guy implements. Oh, right. I forgot about that one other thing, which is interface/. Okay. So number map here is implemented with a mixin, specifically the AVL tree. It contains a key interface, and this, notice, is not a parameterized interface. It doesn't actually allow you to use the parameterized version. A-list is more of a parameterized interface, and we'll touch base on that. So when we talk about parametric polymorphism, especially if you're coming from languages like, say, C++ or Java or C Sharp, or even Haskell has a variant of that as well. ML has something like with functors where you can actually do this. The idea of parametric polymorphism is that you can instantiate a interface into a more concrete implementation by passing in the types of parameters that adhere to some sort of type specification that is required for it to do that, for it to instantiate itself. And we'll see an example of that. The more canonical example is what we saw before in my example with the templates. And there are other cases where we're doing there. But in addition to that, with respect to number map, there is this ability to actually mix in classes into this. So it's taking advantage of the fact that with the common Lisp object system, you can actually define some default implementations of lower level, I would guess, say lower level primitive operations for your specific type of class object, and you could just inherit that functionality for free. A common example for folks coming in who've never visited, who's never seen mix-in programming is, take for example, creating a socket server. A lot of times, regardless of whether or not you are using TCP or UDP sockets, start, stop, listen on connections, which most of which are implemented using the same API and same set of operations. They can be essentially commoned out into this, refactored into this common class that can then be inherited and mixed in. That functionality can be mixed in. You don't have to go and implement that functionality directly. That functionality you get for free from the sheer fact that you're inheriting from that object, which has its advantages and disadvantages if you're using inheritance hierarchies. But with common Lisp object system, because of the way the machinery is hooked up for generic function dispatch, mix-ins is a commonly implemented design pattern so that you could keep common functionality in a single place rather than having the same functionality in multiple places and have a maintenance nightmare in the long run. One particular reason why I'm showing you number map and its implementation, the interface definition, is specifically line 117. Now, we've talked about class allocation quite a bit when we visited Common Lisp Object System, and we've explored the Common Lisp Object System object-oriented programming. But in a lot of cases, we never actually used it. So I'm just going to briefly review what this is. By default, most slot variables in the Common Lisp Object System are defaulted to having allocation type instance, which means when the object is constructed itself. Okay. When an object is constructed itself, it will go ahead and instantiate those slots. That is, unless you specify that the allocation level of a particular object is at the class level, which usually means that there will be, one instance. You could think of it like a class-defined variable from other languages, and that interface, that slot, is now accessible by all instances of this particular class. Now, the reason why I say class here instead of interface is again, although in the Lisp interface library this is defining a set of operations, it is in the Common Lisp object system. It just compiles down to essentially a def class here. Not to say that folks who are application developers should recognize that and take advantage of it heavily beyond that. I would suggest you to look at the and adhere to the API definitions. That is, define your methods using define interface method, define your generic operations using define interface generic, which is part of the Lisp interface library. But this is the reasons why for the slot definitions in the given interface object itself, this is class allocation is available for you. Now, one more thing to mention here is this actually is what implements parametric polymorphism. So in define interface, after the super has the author likes to call it the super interfaces, which is like the superclasses of this interface where it's subclassing from. The list of slots, if there is a non-empty list of slots here, as we could see here, that list of slots is what's used by the underlying Lisp interface library machinery to instantiate new versions of the class of this interface object based on the types that are being passed. That's very important when you're talking about parametric polymorphism, because that means if you're changing the way a key interface is representing, in this case, as you can see, we are our init form is number string map, which I don't believe is defined in this class. It's defined elsewhere. Actually, let me see if I can pull that up so that we can actually get the differences between that. Where is that defined? String map. That is defined in pure. No. Interesting. Looks like number map is the only one that gets. Okay, that makes sense because of the fact that since you can hash or do some optimizations on this number, you can actually go ahead and define it as a special implementation of this. You would have to implement essentially string map with a specific hash function to actually go in and handle that. So it's slightly different. Let me see here. String map. This is also implemented like this. Okay. All right. So I take that back. The reason why this is specifically defined this way is because although it is parameterized and you can actually use this and get different instantiations for numbers. Remember, there's different types of ways you can implement this. You can use this using fixed nums. You can implement it using floats, doubles, and so forth. In the case of strings, which I thought was the case they implemented different hash functions, it looks like they are actually just using basic common Lisp's equal, well, specifically string equal to actually do the comparisons for the lookups. But that may not be the case if you want to switch to other encodings, because although I'm not entirely sure how it works around the scenes, but although Unicode is built into SBCL and many common Lisp nowadays, I think still when it comes to EQL and string equals, it does not do a rune-based comparison. It still does a standard character comparison, which might throw things off since Unicode characters are 2 bytes. But don't quote me on that. I'm just briefly reporting my understanding of how all that works. So we have these interfaces, we talked about parametric polymorphism, but we haven't actually completed one more thing when it comes to defining these interfaces. And it has to go back to, I think, the Lisp Yeah, it has to go back to this particular method again, this interface definition for a list. So although we have an implementation in the case of maps and tree maps to actually go in and parameterize on keys, there's an additional thing that you can do in the Lisp interface library that is particularly useful, and that is you can provide essentially type constraints on those parameters, mainly in the case of those slot definitions, and in the case of what constraints they need to adhere to in order for the actual interface object to be instantiated. And what this parametric keyword does is it allows you to define such a function. Essentially, it will generate the function, so to speak, for you, such that if the key interface, or the slots in these cases that represent the parameters for the instantiation of this interface, if they adhere to these constraints here, in this case, we're specifically saying the key needs to be some sort of equal type interface. Top level could be EQ, but the default is usually EQL. EQL, if you look at the interface hierarchy that's defined by Lisp interface library, it tries to adhere to the common Lisp definitions as provided by the hyperspec. So EQ and EQL and equal are in that order in terms of how they would be inherited from each other. Although I think EQL and equal are actually siblings in this particular hierarchy, at least from the paper that I was reading that I have posted on the YouTube description. But once these are actually adhered to, it will go ahead, as you see here, it is making the actual interface object, okay, itself. The A-list interface object is actually going to be created using this parameterized lambda function, and it's using make interface which is defined in the library to create these interface objects. It's kind of a constructor for all the interfaces, and it will go ahead and then pass in the key value pairs there. So now you can construct this interface object and then use it in a lot of other cases. Obviously, in this particular case, we've talked about singletons before, but briefly, this keyword singleton basically is saying that when this interface object is constructed and is memoized, only one instance should be available. So whenever you pass in this interface to other functions, other generic algorithms, it will recognize that instance and then just retrieve it rather than actually reconstruct it if it needed to. Beware about that because of the fact that if you don't do this and you pass in an interface that doesn't have a singleton on it, you will, as far as I know, get an error saying that you didn't construct an instance of the object. So it'll complain. So if your interfaces, if you know that your interfaces are going to be singletons, please go ahead and mark them as such. That's a pretty important thing to do. Just make sure that I didn't miss anything here. Yeah. The other thing that the singleton option does is it defines a special variable automatically, and that special variable is what you would use every time to retrieve that object when you're passing it into other generic operations. One advantage of this is obviously you can have these top-level arrow interface objects, and anytime you call this interface object here in any of the functions, it's the same as if you are attempting to actually create an instance, and behind the scenes, the machinery will go ahead and check to see if it's already been constructed and just do the retrieval stuff for you. Okay. So let's go back to what we were talking about before. I know I've been digging quite a bit into some of these some of the more nuances of this library and its implementation, but I want you guys to get kind of a clear picture on some of the design methodologies on some of these interfaces, because that was confusing me when I was first looking into this. But then when it became clear, I was like, okay, I see what he's attempting to do. This is making a little bit more sense to me. I'm still working out some kinks on some of the implementation, on some of the availability of certain classes, just because I'm not familiar with some of the concrete versions still just yet. But are there questions? Okay. And so let me just get myself back to this. Just give me a few minutes here, just 1 second. I'm just looking at my notes here. So one thing that I think is important to be aware of is that the advantages of using the Lisp interface library as it stands today, at least in terms of these concepts that I brought up, is one can clearly see that once you've essentially, implemented the basic operation here, as is the case for lookup, and you have this interface hierarchy that has the set of operations as defined by map, which number map, string map, and so forth implements. You've detached yourself from the underlying implementation of the actual data structure and its operations. Now, many of you who have used languages that that support some form of parametric polymorphism know the advantages of using it this way, especially if you design APIs that adhere to this. Specifically, when you're talking about generic algorithms that can work on a variety of data structures, where you don't need to be particularly aware of the underlying semantics of the data structure that you're using. Now, it might be the case that you want to know from a large-scale software perspective whether or not you're dealing with an immutable data structure or not. But this gives you the ability to at least control the state management in such a way that if you need to switch over to a stateful version of something and then back to a pure version, you could certainly do so. And one thing that I want to bring up is the different interfaces that allow you to do that. Okay, so in the case of what we've been looking at so far, the map interface, all right, there is a couple of things that you need to be aware of with respect to this switching between functional and persistent data structures and stateful data structures. Specifically, depending upon the use case, okay, whether you're doing read-only access, you're trying to actually just adhere to actually looking up some stuff, retrieving some stuff, doing some sort of operations, whether it be map, fold left, fold right, and so forth, all of which are available in the library, versus whether or not you're doing sort of an update sort of function, you'll get different return values specifically associated with those types of use cases. Okay, so I'm gonna stop talking in terms of concepts and kind of give you kind of a brief example of this. Okay, we've already looked at this here. I'm gonna first create, for our purposes, a actual map instance of this. Let's do example map, and let's grab this guy. Okay, cool. Now, as you can see here, I'm just showing you, this is just when you instantiated this map as a number map internally, it gets converted into a ABL tree node. There are different implementations of different data structures that are available at your disposal. I suggest you look at what mixins are actually available in the library, and there are a lot of them, before you try and implement your own. And we will touch base hopefully next time. I don't know if we'll have time to actually cover implementing our own interfaces, but I'm just going to show this one here. But we have this example map that we're going to touch on. All right. Right now, this example map is, like I said, a pure data structure, which means when you call up lookup and you let me go ahead and use the REPL for this guy. Okay, let's do this. So that means when you call lookup, again, you have to go and provide our map, and we provide our example map here, and we provide our year key. Well, let's use name key here for the sake of example. You will end up retrieving this, and you know that obviously when we call example map, nothing actually got modified. The same thing is if you go in and let's change this example to let's call the same thing as it occurs is let's call map a list. Okay, map a list, which again takes actually, let's not call map a list. Yeah, no, that's fine. If we do a list, and we call the map on here, see what happens. It's not of type sequence. What was it? a list requires a sequence. That's interesting. Hold on a second. Let me just pull up something here. Map checking variant. Okay. Let's go to here. This is our might be messing that up here. What was that example? It was, let's change this instead of map a list. Let's do pure tree map 2. There we go. Let's do this too. This is a function, but this is going to go in and actually map two different maps together based on the arguments. That's not what I want. I wanted essentially to do a transform on this guy and do the key value pairs. I might be using the wrong method here. Give me just 1 second. Update height pair. So yes, all copy, join, left, make, move, right. Let's use order. This should be descending order. No, that's not going to work because I don't think that's orderable. Let's try. As you can see, folks, I still am not familiar with where all the maps go to associated with this because some of them are doing one thing versus what I think it should be doing. So like this one, if I do, let me see if this works. Pure a list example map. Of type sequence. That means this is not adhering to the example that it's expecting. Interesting. Okay, I'm going to move on. I will go ahead and look up some more examples, some concrete examples for read-only access. But my point is that this number map is always going to be unmodifiable, and we'll see this at least with the read-only ones. It's obvious to see that nothing will get modified. But what if we wanted to actually insert into this? So an example of that would be if we use interface all insert. Sorry, shouldn't be interface all. Should be pure all insert. Now we will take in our case, our pure tree number map that we do. Or we can use the shortcut number m, which is the same. We take in our example map, pass in a 4. Our value is going to be another test. And we'll see that it will go ahead and insert that into the tree. But notice, just like our other functional data structures that we saw in the past, the original tree isn't actually changed. What if we want, though, and this is the beautiful part about this, what if we want to change this to be stateful, right? Well, we could first create simply a stateful lookup. So instead of doing this, okay, we do this and change this to a stateful example map, okay? And we, hold on, let me just change my indentation so that it's a little cleaner. We'll use, instead of pure A-list A-map, we do stateful A-list. Interesting. Sorry, pure, should be a pure A-list. But here, let me see if I can just go to stateful tree number map. Okay, this should work. So again, you can see that our stateful guy is now that. Now, if I just change simply this to being stateful, and again, we need to have the stateful instance, and we go and insert into it. What did I mess up? Oh, my apologies. I have to actually also change this to stateful too as well. Now, hold on 1 second. This guy has to be changed just slightly. So now, if we look at stateful sample map, you will see that the actual change has occurred. Now, a couple of questions are already probably boiling in folks who are joining in or who are in the audience right now. One, well, it's a different function call. You're not actually changing much in here. Well, yes and no. So this is actually illustrating one thing that's inside of the library itself, and that is there are two distinct approaches, either when you're dealing with pure data structures or stateful data structures, and it's mainly related to the fact that stateful data structures, since you're modifying the data structure in place, you are going to get a different return value than what a pure data structure does. As you saw in the pure data structure case, just like our other functional libraries that we've touched, FSET, Sycamore, and so forth, it does not modify the actual data structure to return a new instance of a data structure for you. In the case of stateful, as you saw, it is actually modifying it. Now, this is a single API with different return values for two different use cases for this. So if you're trying to mix and match there and saying we're going to do pure and stuff, and you have the same API, but the return values, since they've changed, the author decided that the best way to make sure that you are aware of the distinction of the return values especially is by packaging all the stateful stuff into one library and then package all the pure stuff into another library. Well, in the case of Lisp, the stateful stuff is in one package and the pure stuff is in another package. Does that make sense for folks? One of the nice advantages of the fact that we've essentially separated the two is and this is again the design stuff that I'm just going to mention from the paper that I read, and that is all the interfaces in both libraries will have identical like signatures one. So you can actually, with very minimal effort, convert from one to the other. But because they have return value changes, it'll become clear from the return value that you're using whether or not you're in a stateful mode or in a pure mode. Which is, I think, very useful, especially when you're maintaining a large enough code base that's doing some of this stuff. It becomes clear that where side effect code is actually occurring. All right. Now, if you are actually doing this, this will allow you to actually go in and do sort of what I was kind of alluding to with some of the examples. Let's hold off on it. This allows you to adopt certain Haskell-based functional patterns. I say Haskell-based mainly because really it should be ML-based, but with static typing, as many of you know, you have this ability to clearly indicate when something is going into stateful mode and when not. Specifically in the Haskell sense, it's when you're going into the monadic world, you're actually kind of assuming that you're doing some sort of manipulation with the state, and as long as the types line up, you're actually okay. Now, I bring that up because what this interface library allows us to do, this Lisp interface library, is that it enables us to actually go and start adopting some of those things, albeit it's going to be a runtime-based check rather than a compile-time-based check. I'm reiterating that specific point just so that folks do not think that this is adding static typing into Common Lisp. I mean, Common Lisp already is a strongly typed, dynamically typed language. And its advantages of being able to being in a REPL and being more interactive certainly gives you certain advantages that I still believe that other library languages still do not have to date yet, with the exception of Smalltalk. But this library gives you the ability to, at the very least, adopt that design style and create code that clearly separates your side effect code from non-side effect code with a more universal API. And it follows kind of in line, if you actually think about it, with how Common Lisp separates its functional API from its non-functional API. And I'm thinking of functions for folks who are not aware of like nconc, which is the concatenation for that destructive concatenation versus concatenate or conc. Or even a better example is reverse versus n-reverse, which is in place reversing of a sequence structure versus doing a functional-based reverse and creating a new version. There's certainly analogies with what's currently available in the API than what we're currently using today. So I'm going to end it here. I appreciate you guys for joining me today on the.
Hello, just got here.
Oh, hey, Michael. We're just finishing up. Next time on it, I want us to cover interface transformations, which is also part of the Lisp interface library, and hopefully, I will also show you how to create your own versions of some basic interfaces that are first class that will allow you to create some generic functions of your own. And I will, by then, hopefully get a better indication of what is actually already like implemented at your disposal of the existing interfaces, so like concrete implementations of these classes. And that way you guys can certainly just start using those directly rather than implementing your own. And then that should hopefully set the stage for another set of talks on this library, which is mainly related to being able to design functors applicative. Well, I know at least functors are available, and there are a couple of monad transforms in this library that I'm excited to actually go through. But this foundation is required in order for us to go into that realm can start exploring, because honestly, without understanding some of these concepts, it is definitely an uphill battle in order to start going full force on some of the more advanced features of this library. Any questions? Cool. So